This is a joint work between Southern Illinois University, University of Stuttgart, and Karlsruhe Institute of Technology. Today, we will present our work titled Positive-Negative Approximate Multipliers for DNN Accelerators. With the recent and rapid advancements in the area of machine learning, deep neural networks are constantly evolving, becoming more and more computationally intensive in order to accommodate the latest research and industry accuracy requirements. During the inference phase of neural networks, the dominant arithmetic operation is the multiply-accumulate operation. Therefore, embedded devices integrate DNN accelerators as a solution to the throughput latency requirements. But even though the hardware accelerators might be a solution, integrating thousands of Mac units in order to keep up with the computational demands results in increased energy consumption. An important question we're being called to answer is, how can we trade off the system's energy efficiency with respect to the DNN's accuracy? Previous research works have shown that a great amount of DNN computations can tolerate at least some degree of approximation, thus reducing energy consumption without sacrificing the end and inference accuracy. Thus, by exploiting the principle of approximate computing and by designing and developing approximate multipliers, we can achieve considerable energy reduction with respect to the entire accelerator. Current techniques for designing approximate multipliers mainly focus on the introduction of low error and also apply retraining to recover the accuracy loss. However, this is not always feasible due to proprietary datasets and models and increased training time for deeper networks due to the approximate multiplier simulation. In this work, we design an approximate multiplier that approximates the generation of the partial products and comprises three operation modes: the zero error mode, the positive error mode, and the negative error mode. Then, by approximating more or less partial products, we control the applied approximation and tune the accuracy-energy reduction trade-off as required. Finally, we present a methodology where for each NN filter, we exploit the two synergistic modes of the presented multiplier and group all the weight values into two balanced summation sets, with the final goal being the convolution error converging to zero and consequently achieving high inference accuracy. We will now present a brief overview of our methodology. First, we show a rigorous error analysis that is exploited in the error optimization of our mapping methodology. Then, given a trained neural network, we quantize weights and activations to 8 bits and apply a mapping methodology, on which we will elaborate more later on. First, we will present the error analysis that supports our approximate multipliers design. The most complex computation in the CNN inference phase is the convolution operation. B is the neuron bias, W are weights, and A are input activations. We denote as epsilon the error of the approximate multiplication. By eliminating the generation of some partial products in a multiplier design, there are less partial products to be accumulated. Therefore, the error epsilon when eliminating Z partial products is the following, with this average and error variance. In our work, we control the number of approximated partial products at runtime and support three modes: zero error, positive error, and negative error. The ZE mode refers to the exact operation. In the PE mode, the Z-least partial products are perforated, and in the NE mode, we force the generation and accumulation of the Z-least partial products. Therefore, the average error and error variance for each activation input are shown here, where S equals to 1 in the PE mode, S equals -1 in the NE mode, and Z equals 0 in the ZE mode. We will now present the filter and weight-oriented approximation method we used to map the neural network weights to the appropriate modes of the presented multiplier. This procedure aims to satisfy a given accuracy drop threshold while maximizing the number of weights that are assigned to the high Z values. For our analysis, the available values for the Z-least partial products are 1, 2, and 3. Our method comprises a total of 5 steps. In step 1, we want to identify how error-resilient each convolution layer of the neural network is. We initially consider that all weights are assigned to the ZE mode, and for each layer of the neural network separately, we count the occurrences of each weight value per filter. We take advantage of the positive-negative architecture of the multiplier and assign half of the weights to the PE mode and the other half of the weights to the NE mode in order to cancel out the introduced error. If a weight value exists an odd amount of times, we keep this extra occurrence in a residue list, unique for each filter, and assign it to the ZE mode for the time being. We call this concept filter-oriented error balancing. We perform this procedure for each neural network layer separately and monitor its accuracy for Z equals 3. This way, we can determine which layers are more sensitive to approximation. The output of the step is a list of convolution layers sorted based on their error resilience. At the second step, we want to determine how many layers can be mapped to high approximation simultaneously. Starting from the most error-resilient layer towards the least resilient one, we map the convolution layers to the PE, NE, and ZE modes as described earlier, while still using Z equals 3. We stop this procedure once we reach the accuracy drop threshold. At the third step, we repeat steps 1 and 2, but this time we change Z to be equal to 2. And we only apply the steps to the layers that haven't already been mapped to Z equals 3 from the previous 2 steps. Usually, after this step is done, some of the layers of the neural network are mapped to Z equals 3, some to Z equals 2, but some are still entirely mapped to the ZE mode. At the fourth step, we map the ZE layers to the PE and NE modes with Z equal 1. Since this new mapping can, however, impact accuracy, we also start an exploration procedure where we move layers from higher Z values to lower ones. First, we move one by one layers mapped to Z equals 3 to Z equals 2, and then we move layers mapped to Z equals 2 to Z equals 1. Finally, we move layers mapped to Z equals 3 to Z equals 1. We keep all mapping combinations that satisfy the accuracy requirement and will in the end create a Pareto front. At the fifth step, we partition the residue list of each filter into 2 balanced summation sets using the largest differencing method, and we assign the first set to the PE mode and the second one to the NE mode. We start with Z equals 1 and move our way up to Z equals 3. The achieved energy reduction of the PE and NE modes for different Z values are shown here. The energy gains increase as the value of Z increases. However, the magnitude of the multiplication error for both modes also increases. The efficiency of the error balancing, that is, how close the average convolution error is to 0, depends on the weight values. Weight values close to each other increase the probability of error cancellation with our positive-negative approximation. As an example, the GoogleNet weight value distribution for the CIFAR-10 dataset is shown below. The distributions, which are shown per layer, are close to normal, and the weight values feature low dispersion. Since MAC operations consume a very significant portion of the total energy cost, we evaluate energy reduction with respect to the MAC operations. We present comparative results against a variety of state-of-the-art techniques and consider the 7 deep neural networks and 4 datasets as shown. In all experiments, 8-bit post-training quantization is used. The first method we consider is the exact method, which uses an exact 8-bit multiplier and is a baseline for our experiments. We also consider the all-one method, which utilizes multipliers from a state-of-the-art library and employs weight tuning to minimize the error that the approximate multiplications incur. We consider the more fine-grained weight mapping approach, which is described in LVRM, which employs a low-variance reconfigurable multiplier. We also consider the convar method, which achieves high energy gains due to high approximation at the multiplier level. Finally, we employ the concept of the largest differencing method on all the weights of all layers of the neural network, instead of applying this concept only on the residue weight as we do in our methodology. This figure shows the energy savings for the CFAR10 dataset. Across all 7 neural networks, our approach achieves an average of 17.43% in energy gains for all the considered accuracy thresholds when compared to the exact mode of operation. We observe that the energy reduction gains increase as the neural networks become deeper with more layers, for resin 56 for example. All1 and LVRM achieve on average 3.77% and 11.57% gain in energy respectively, while Convar sustains a 19.2 gain in energy, surpassing our method's results by 1.77%. FPS resulted in an average of 7.8% in energy gains. The next figure shows energy gains for the CFAR 100 dataset, where the achieved gains are the lowest you observed in our evaluation, since it's a more challenging dataset. Our proposed method still attained an average gain of approximately 15.33% across all neural networks and accuracy thresholds. LVRM maintains energy gains above a minimum 11%, without, however, achieving energy gains above 13%. For the MobileNet V2, our method achieves similar energy gains to LVRM, and for the ResNet 20, LVRM surpasses our method's gains by an average of 4.5% for the 3 accuracy thresholds. Convar could not satisfy neither of the 0.5% and 0.75% accuracy thresholds for ResNet 44, yielding no results in these cases, ending up in an average of 17.37% in energy gains for this dataset. Similarly, FPS did not produce acceptable results for any of the accuracy thresholds for GoogleNet and ResNet 20, and only satisfied the 1% threshold for the MobileNet V2 and ResNet 32 neural networks. This figure depicts the energy savings for the GTSRB dataset. Our proposed method achieves an average of 18.71% in energy savings across all neural networks and accuracy thresholds, while LVRM and All1 achieve 11.81% and 3.44% respectively. The lowest observed value in the attained energy savings of our method is approximately 12% for the MobileNet V2, while the highest is 23% for GoogleNet for the 1% threshold. Again, Convar could not produce an acceptable result for the 0.5 threshold for ShuffleNet, ending up to an average of 18.29% in energy savings. FPS also failed to produce acceptable results, specifically for ShuffleNet and for all the considered thresholds, resulting in 9.98% energy savings on average across the dataset. Finally, the corresponding results for the LISA dataset are shown in this figure. For this dataset, our method achieves the highest energy gains that we observed throughout our evaluation experiments, being 21.86% on average across all neural networks and thresholds. In this dataset, LVRM and All1 achieve 12.57% and 7% respectively. For the 0.5% for MobileNet V2, Convar again failed to meet the requirement, and it did not result in acceptable accuracy, ending up to an average of 18.29% in energy savings for this dataset as well. Likewise, FPS did not produce any acceptable results for none of the considered thresholds for MobileNet V2, ending up with an average of 9.94% in energy gains. Some remarks regarding our evaluation. The methods we included in our comparison did not require retraining. Our method resulted in solution mappings that respected all considered accuracy thresholds for all neural networks, yielding high gains in energy for every case. On average, our method achieved 18.33% while Convar yielded 18.29%, LVRM 11.9%, FPS 7.46%, and AL1 4.27% in terms of energy savings. Convar was the method that reached and maintained energy savings similar to our proposed methods, in some cases surpassing our results by up to 11%. However, Convar failed repeatedly to satisfy the given accuracy thresholds, as opposed to our technique that always satisfied the accuracy constraints. By pushing the approximation more, we were able to counteract smaller energy gains in some cases with greater gains in others, reaching average energy savings similar to Convar. FPS also failed to produce acceptable solutions on multiple occasions, justifying our choice to only employ LDM on smaller sets of weight values in the final step of our mapping methodology. In this work, we presented an approximate multiplier that can be reconfigured to generate positive, negative, or no error. We also proposed a filter-oriented mapping methodology that aims to satisfy a given accuracy drop threshold while maximizing the applied approximation, targeting high energy efficiency. Our extensive experimental evaluation shows that our filter-oriented approximation with our positive-negative multiplier outperforms significantly state-of-the-art, while always respecting accuracy constraints. I would like to thank you for your attention, and I would be glad to answer any questions you might have.